operation. So this comes from a paper. I see this on the end of the slides. My idea was to replicate this board. So, but the first question, why I want to make a board? Why I want to do this? What is this? Is the first question. So, a little bit about story. I was helping a friend in my hometown. This is my friend Edney. Was actually one of my physics teachers from the high school, and the guy that made a significant impact on my life. And I was helping him with like the troubleshooting of some board. This board from the IFO 2017 is a teslometer. I was making like debugging the teslometer, and I was discussing for him, and he like called me and said, "Oh, I want help with this." And also, I found an amazing article about Bulgarian Olympiad in like experimental physics, and they made like a very good project that I want to bring to the students. So he asked me, "Could you make the board for me? Do you know how to do this?" And I said, "Oh, I never did it before, but I really want to try it." So this was the start. And the first question, what this board does? The board is intended to make an experiment to determine the Boltzmann constant. So the first thing is, what is the Boltzmann constant? And for the this very short group of slides, I will ask you if you guys, the people that don't like much of physics, I will just make like a very simple introduction just to explain the phenomena, because the whole point of the board is to determine the phenomena, and I think it would be very important to make this like short explanation. So the Boltzmann constant is one of the fundamental constants of the physics, and yes, it's quite small, and it's for the education purposes. It's very good to make constants and values of physics that seems like magic for the students. It's good to know how this exists. I can measure. This is the point of experimental physics. So this is the idea. Following the original article, it said that Einstein in 1902 proposed that in theory it was possible to determine the Boltzmann constant by evaluating the mean of the thermal energy. That's the main point. This is what they actually proposed. The original article is in Deutsch. I don't speak Deutsch, so I believe you what the people from the article said. But the original paper is available. The people have no Deutsch. But okay, the idea is to determine the Boltzmann constant by the means of the thermal energy. But how we can do this? To understand this, just to see a simple resistor, a single component that you can see, because of the random movement of the electrons, this resistor makes you can see a slight fluctuation in about of attovolts, and this fluctuation is known as thermal noise, and the thermal noise is because of the movement of electrons, and it's relating to the thermal energy. So the idea is to measure the noise, but the mean of the noise is 0. How we can do this? We need to see the power of the signal, the power spectromicity of the signal. So yes, looking at this, you guys don't need to know the math of this, just to know is this the power of the signal. And looking with this, we see, we have a value we can measure, and the most important thing is related to the Boltzmann constant. Einstein was right after all. But have some issues. The first issue is that, as I said, is in attovolts. This is nothing. We cannot measure this taking a multimeter. It's not possible. And also we have dependency of the resistance and the frequency of the noise. As the main point is that these things makes the experiment unfeasible in this way. So the idea is to put a capacitor, and with this, when you make the new PST of this signal, of this voltage source, you can see that the mean square voltage that you see in the end is depending of the Boltzmann constant, is a bigger value, because using a small capacitor you can increase this to nanovolts, way better. But I will get the point when you can measure it with a multimeter, but way better. And we get out of the dependency of the frequency and the resistance. So very good. A capacitor is way well behaved than the resistor. So this is the main point. And for you guys, this is what I want to measure with the board. So the mean square voltage of this signal. And this is the resistor. It's just divided in an ideal resistor in a voltage source. But and this is the original layout. So we are getting to the layout. We're close to KICAD. this was the original layout proposed by the people from Sofia University. My idea was to replicate this thing. And for this, just explain this, the value, the mean square voltage value is actually in nanovolts. It's quite small. This step here just amplifies this by 1,000,000 times. So we get from nanovolts to millivolts, a measured value, yeah. And in this part of the circuit, this here, just make the square part, it's a voltage multiplier, and in the end, just a low pass filter for the guys who didn't know electronics, but this takes the average. So yeah, in the end, we measured that thing, the mean square voltage of the signal. We can, with this, determine the Boltzmann constant. Okay, you guys understand the idea. So, okay, let's do the board. KICAD. KICAD is a cross-platform open source electronic design automation suite. I choose KICAD because my friends used KICAD to design some boards, and I want to try the software. And it's also very beauty. It's very intuitive, and it's come close to like a professional tool. It's actually a professional tool to design circuits. It's close to Altium. Altium has more features, but for me, KICAD is like in the same level of Altium. So, okay, let's design and order the KICAD. Design with KICAD, we get this like the intro screen, and we have a lot of features to access here. The first thing that I want to do when to make a board is the schematic part. So this was the original idea. But how we can do this in KICAD? The idea is like to open a blank canvas and start to placing the components in the correct way. You choose the component, choose the specification, see for example the fabrication that you want. You can import some external symbols from the manufacturers and make your board. And this was my schematic. A lot of work to do. It's not like you jump from one to the other. And yeah, KICAD is a very powerful tool to do this. You can make comments, draw the things, and also one important thing: when you end your schematic, you need to check if it's right. It's right. So KICAD has a powerful ERC checker. This is common in professional tools, and I would like to highlight this thing because the points that I will highlight in the presentation that make the KICAD, as I think, a professional tool to work with circuits. So you can, for example, check if you misconnect something is unconnected, something is short circuit. It's a very powerful tool. When you miss, you can configure the warnings, like the errors, the class of the error. And when you make a mistake, for example, this mistake here, it's a point here, explains, and if you click, they go right here and explain, oh, you short circuit this. You are sure that you want to do this, and you can, for example, oh, no, I want to do this, and just disable the warning. But very powerful tool. This verification tool that I will talk in the presentation is the thing that makes is very important to professional design. So okay, this thing, and KICAD also has a simulation because we checked that we corrected things right, but it behaves the correct way. Simulation goes with this, and one of the things that KICAD is very good, and I think this is recent feature, was not available in the past versions. Is like a native integration. You don't need to export like a SPICE model and simulate in an external simulator. It's integrated itself. I used KICAD version 7. Version 8 is way better, but I will discuss issues with simulation at the end of the presentation. But this, for example, is an AC analysis of the gains part of the circuit. I have some issues determining the simulation of the whole board. But I will get this in a later part. But for example, this is a working simulation of the entire circuit. So I could check, oh, it's behaving as expected. And for example, I was with some questions about the behavior, and I could see in practice, oh no, yeah, it's working like this. If I change this, the simulation will behave differently. So very good tool and very professional. So okay, we made the schematic. We checked the components. We have a working circuit in theory. How we can make it to work in the real life. We need to make a layout. The layout is when you pick the schematic and I want to place in a board that is actually manufacturable. So the KICAD has a layout part. You start with a blank canvas, and you guys can think, I need to place the components all again. No, KICAD is going to help you. You can import the components from the schematic and just click a button on there on top here, and you just can import all the components. Just click update, and they are here. And it works when you change, for example, something here on the schematic, you can just put in the layout like straightforward. It's not on the only on the start. You can the two of them are coupled. This is very interesting thing. So yeah, you put the components on their layout, just place them where you want, define the edge cuts of the board, put some pads, and yeah, you actually have a board. So with this, you can, for example, make a silk screen, like good things to put on the board, like some drawings, some explanation of what things are, and you can put all of this. With this in mind, you can, for example, start the routing process. That is like putting the wires, the tracks on the board. And for example, if you want, oh, I want my power tracks way much wider than the signal ones. I want like I have a special connection. I want to make in a specific widths. How you can do this? So KICAD can like make classes. You can specify, oh, I want the power classes to be way wider. The standard ones in the specific way. You can change this, and with this set, you can just like browse normally, and the KICAD will take the work to choose the correct width to the tracks. So very powerful. And just make the tracks. You have this like this board, and with all of this made, you can, for example, make the ground planes. It's very important to circuit design. With the ground planes correct draw in the board, you can with this you actually have a big capacitor because you have like a ground plane on top, a metal plate on the top, metal plate on the bottom, and a dielectric in the middle. For you guys that know that electronics is a big capacitor. We don't want to do this. And to correct this, we can make like little short circuits on the board. This is known as V-stitching. And in the old days, you do this manually. So you can start with the V's, but this is like, no, this is not an engineer's job. This is like a technician job to do. And KICAD also has can get a hand with this. Because they have nice KICAD add-ons. There is like plugins for the KICAD. Because KICAD is scriptable. You can like make scripts, and you can share the script with the KICAD add-ons. So you can have, for example, new capabilities. For example, you can actually make KICAD to do like parasitic extraction. That is not so common, I think, for PCB designs, but for semiconductor like designs is very common. But you can implement this. Actually, KICAD has one of this. You can make like automation tools, as I will show here. And for example, you can share your 3D models, your symbols, all of this, and also share your color schemes. Why not put a Dracula scheme on the KICAD? You can. You actually can. So okay, you go to the store. This was the old store. I think the KICAD 8 has like a way beauty store, but you choose your plugin. This is my installed plugins. The repository has 81 plugins. You choose this one. This is the KICAD action script. And with this, just specify the parameters of your V-stitching, the distance between them, the clearance, all the things, the pattern that you want to do, and it's done. Actually, this is the V-stitching feed made with the tool. Very very fast, very powerful, and they generate like vias that are separate from the design. So if you have vias on your board, they will not interfere, and you can like, oh, I don't like this pattern. You just can erase the vias that generated and put it again. Very powerful tool. And this was one of the features that Altium has. People, oh, Altium is way better. But yeah, KICAD also has this feature. So very, very important. And this is the final board actually. With this, we can make another checking part, very important to design because the idea is to manufacture this board. So to manufacture, we need to like make it physical. To make it physical, someone needs to make the board, fabricate the board. And the manufacturer has some limitations. How thin the tracks can be, how small the holes can be, all the things. And to make is my layout correct, you can have the DRC. DRC is like in the semiconductor part, like microelectronics industry, it's way like more complex. In PCB, it's way simpler. The main points of the DRC is to check for geometric constraints. You don't like it's not usual to check for parasitics and etc. But yeah, limitations on geometry, and also it also performs a DRC to check if you, for example, as I said, oh, I want to connect this part and that part with the circuit. And for example, I forgot for some reason. The DRC will warn me, oh, you not connected this. Are you sure it's correct? And for this, you can, for example, about the geometric constraints that I said. You can use a UI. It's very intuitive. We can just check, for example, the fabrication like website or data sheet, put the rules here, and you have like a DRC working. If your, for example, your process is way more complicated, and you still want to use KiCad to do this, you can actually make, for example, custom rules, and that is not on the UI. So make custom rules. This is the GLCPCB custom rules. For example, they have like different rules for different layers, and you could just put this on your DRC, and it will work by like straightforward. I not writing this on my own. The reference is on the GitHub. My GitHub repository is where I found this code. It's for some guy in the GitHub, and yeah, you can do this, and the DRC will work. This is like an unconnection circuit. This is warning me, missing connection between items. Very intuitive. This is like, I will emphasize this because some tools are, the error is not intuitive. They don't say, an error, find yourself. They both know, but this is saying, is this thing unconnected? And very clear, very easy to work, very intuitive. And this, for example, is a constraint violation. They're saying the device too small, and it explained to me what's there, how to correct, and the rule related to it. So, very powerful. With this, all in mind, we checked out things. We have ready to go board, and but I want to see the board, to see like previous, to know, to have an idea of my project before making to manufacture. You can use 3D visualization. That is, it supports ray tracing. It's very, very like beauty. I think it's better shown to than talk. And this is a 3D rendered by KiCad of my board. I have the board here. I forgot to bring the board here, but it's in my backpack. But yeah, this is the board, the 2D visualization. This is the board with all the components. The back part. Very beautiful, very like powerful tool, very professional, all the features. And yeah, I talked about KiCad, I talked about the project, and what the issues that I faced. Is KiCad perfect? No, actually don't. But it's a very good software, very powerful one, but I need to like make my complaints about it. The first complaint is that multi-project on KiCad is like painful, because you need to work with yourself, the different projects, and if they relate to each other, you need to make the unity at your own. You need to manually put the things. KiCad could help with this. Autumn had the scalability. I don't know how why KiCad does not support this. I don't know, maybe. No. Other thing was the simulation. On KiCad 7 it was like pretty worse. I would put more like complaints about it, but I checked in the version 8, that is the current version, and they correct a lot of things. So the 7 version is not so great. The documentation, I think they are missing some things, but I say the documentation is missing because the starting documentation is way good. It's like a very good tutorial. Goes a lot of features on the project, and I'm just saying about the documentation because it's not that it's like horrible. It's because compared to other documentations, it's like missed some points, and could be better. And the other things, even with KiCad 8, my whole simulation was not working, probably with some model issues, but I think it's like a limitation of the simulator, and this is not KiCad's fault, but I think, for example, supporting multiple backends could be good. But yeah, okay, talk about a lot of things. Other thing was customization was a bit too laborious. You can't customize it, but okay, some issues. And okay, I talked about the issues. Future work is the last part of the presentation. The board arrived to me like yesterday, and I have the board here, but I was not expecting to have the boards as soon as this. But I need to check if it actually works in the real world. Also, I want to reduce the cost, so some changes, but this is iterative design. I also check for design flaws. And other thing, this is very, very good for KiCad and FreeCAD in the open hardware ecosystem, is because you can actually integrate KiCad with FreeCAD and make a mechanical and electrical tool to work with both. And I want to make a support board to my board, and I want to integrate the things, but future work, good thing to do. Very nice that they integrate themselves. And yeah, make the simulation work, why not, in future work. So this is the reference, and this is the end of the presentation. Thank you very much for listening.
Any questions to Carlos?
You're bored.
You're bored. I have a question. You said we're not expecting to have the board so soon. I mean, were you able to test and check?
No, it's actually yesterday.
Okay. Yeah. Because I'm just curious. Because I mean, it's of course important to have a good design too. But usually, as you said, I mean, you have to have few iterations before you get things right. Especially because there are some details that the simulation doesn't show, right, and all these things. So yeah. It would be great to hear from you afterwards about what was the result.
Yeah. So that this, I think, you show it to the camera.
Oh, let me just, yes.
Yeah,
you can show the camera now.
Like this. So the software screen is open, and now you have the board in your hand. So from let's say, consider a student that wants to do the same. How much will it cost for someone that does not have any access to anything to start today and get something like you have in your hand?
Oh, for this, I think my budget to this was like I made it my own. I asked to money for some people, but the budget I think I go out of budget in my designs because I get excited to like make the board beauty and make a good project. So
There's even a picture, right?
Yeah.
That should be expensive.
No, the picture actually don't. But the point is that the size is very big, and this goes to like a lot of.
Do you want to present to the camera? Because now it's getting you.
Yeah. This is the board.
Yeah. You can put it closer. Yeah, that's cool. That's good.
The drawings is not so expensive, but the area is very expensive. So this is the point. But yeah, I think just for the board, not the components. The board was like this size board, and all the small modules that they have. They cost for fabrication on the GLCBCD 200 reais, but the full price was like 400 because 200 in taxes. We are Brazil. Yeah. So, but yeah, very expensive. But for me, it was like I consider itself as like a portfolio. So, and I was like too on the project to go out. But I think GLCBCD actually has like a low price things. I think could be like 100 reais, maybe 200. But I think for the board, in the components, it's other part.
That's quite cheap if you're considering like you're designing some board and some product. I mean, for a starting company, for a startup, that's pretty inexpensive to consider because tooling. I'm not sure if you know the current prices, but 5 years or so, auto design was really expensive. So considering that you're a student, right?
Yeah.
You could afford to design your board, and so I think that the real value here is in the tooling that you use, right?
And we did think that, of course, he's doing this by himself, but if you are a research institute, for instance, usually has tax exemptions, and it will be, less expensive, I would say. So only the license to use CAD's design tools is probably much higher than what you spend. So.
Oh yeah, the license part is the worst part. Yeah, I agree. The manufacturer is like consider a company is like small price, but from me as a student it was like a lot of
considerable price. Yes. Any other questions for Carlos? All right, thank you very much, Carlos.